Hey everybody, welcome to my presentation. Tonight I'm going to be talking about shooting International Space Station solar and lunar transits. If you've never had the opportunity to see the space station pass in front of the sun or the moon, I can guarantee you it's a real treat. We considered changing the name. We didn't want the IRS or the federal government using their search engines and see that we're mentioning shooting the ISS. But after careful deliberation, we decided to leave the name with shooting. After all, we're using a camera to shoot, and I think the government should be able to figure that out. So, without further ado, let's get started. The first thing I have to say in any presentation I give where we're considering even looking at the sun through the telescope is to follow safe procedures, follow manufacturers' recommendations when you're using gear. I don't think I need to go into all the details with you guys because you're all amateur astronomers and I think you all know the rules. I'll just briefly say don't use any kind of glasses except the safe solar glasses that you can buy like from Rainbow Symphony or other places. If you have those safe solar glasses, don't think that it's safe to put them on and then put a telescope or a pair of binoculars or a camera or something in front of them, because that's not going to work. So let's head to the next slide. I want to show you guys a brief video of the last time I shot the sun in an ISS Transit back in March of 2011. When I found out this was happening, I contacted members of my local club, the Black River Astronomical Society, and we all went to Sandy Ridge Reservation to see this event. If you're going to be shooting an ISS Transit, you're going to need a timekeeper or an accurate method of telling time, because these transits only last a very short time, like sometimes under seconds. This is my friend Randy Shivak setting up his C8. Mike and Fred showed up with one telescope. I'm not quite sure how that worked for them. I'm guessing only one of them got to see it. Everyone else had gotten there early and set up. I got there early and was still in the process of setting up only moments before because I had so much gear with me. And you can hear the wind blowing. I included the audio so you can hear our timekeeper counting down the time. It was at 10 minutes after and 37 seconds. So you'll hear him counting down. There's 10 seconds. 15. At this point, I'm under the hood and watching my monitor. 7 seconds till go time. So at this point, I had already started my video. And then in 3/4 of a second, we saw this. And there it is a little slower for those of you that missed it on the first go around.
Well, it was by. I don't know if we got it. Oh, man. I think it was faster. It might have been 7 minutes, maybe a little bit.
So I just have to comment that anytime you see a bunch of 60 and 70 and 80-year-old men jumping up and down, hooting and hollering and clapping their hands, you know something pretty spectacular happened. So I'm glad we did this as a club and got 5 of us out there that were wanting to see it and got to see it, and it's a really good time. So I'd highly recommend that if you see one coming up in the area, call some of your friends up and do it as a group. Well, this is my video of the solar transit, but you just saw it in the other video, and this one's not working. So let's go to the moon transit. That one still works in the program, and you can actually see how quickly it was moving. This one was a little longer than some of the others, and as you can see, it wasn't a full moon. Yeah, it's pretty spectacular. So the question everyone asks is, how do you know when there's a transit coming? Do you use some kind of scientific principles to figure out the dates and the times? Or maybe, just maybe, you have a secret squirrel ISS detecting helmet like I do. No? How about an electronic ISS homing device? I doubt it. So then how do you do it? Did I go online maybe to figure it out? Yeah, I did. Because as most of you know, there's an app for just about anything these days. Matter of fact, there's a bunch of apps. So when you have a bunch of apps, how do you know which one's best? Well, more importantly, which ones are safe? Now, of course, if you use an app, it's got to know where you're at. So you got to tell it where you are. You have to give it your location. If you want it to send you updates when it sees a transit coming, you have to give it your email. But you don't have to give it your phone number. You don't have to give it your phone contacts, your friends list. You don't have to give it access to the files on your computer, or to access the system or your computer, or give it your password. Any legitimate program doesn't need any of that stuff. So I tried several, and the one I like best is ISS Transit Finder. And on the left side of your screen, this is the pop-up window that you see when you open up ISS Transit Finder. Now, to find it, you just go into your Google search and type in ISS Transit Finder, hit enter, and this screen will appear. Now, you have to enter your latitude and your longitude and your height for an accurate determination of your observer location. If you don't know that information and you're on a phone or a computer with a laptop, you can tell it auto detect, and it'll search through your phone or your computer's GPS system and find you and set you up. Or you can select from a map, as you see here. Push that, and a map of the globe will appear. You find the US, find North Carolina, zoom in, find Charlotte, go to your house and select your house, and it will know exactly where you're at that point. Next, you have to give it a start date, finish date. So it defaults when you open up the program with today's date. I usually change it to tomorrow because chances are if it's happening today, it may have already happened, or I don't have enough notice to get ready. So I always start it tomorrow. And it says you can go up to 20 days in the future. Now, the further out you go, the less accurate the program gets, and we'll speak to that a little bit later. And then the last thing is you enter a travel distance. How far are you willing to go from your house? Of course, it'll tell you if there's one at your house, but you can tell it, you can specify, put an 80-kilometer circle around my house. And if it's anywhere within that, so that could be up to anywhere 40 miles north, south, east, or west of your exact location. And actually, it's closer to 30. So that would be 15 miles in all directions. And then you hit calculate. And when you do, the window will appear with what it's found. Now here you can see it found 2 different transits. The first one actually is a miss. So we don't care about that. The second one though, look at that. Space station is going to go right exactly almost through the center of the sun. That's what we're looking for. And it tells us the date and the time right down to the thousandths of a second. And here's the little window that comes up. It tells us the size of the space station, the distance, how far it is from the center of the sun, which is 0.2 arc seconds. Gives us the altitude, the azimuth, center line. Quite a bit of information there. So here, whoops. Here it shows definitions for the size, for the distance, for the angular separation, for the azimuth. Now, azimuth, we're measuring 360 degrees like in a compass. So 0 degrees is north, 90 is east, 180 is west, etc. It says that the azimuth is 75 degrees. That's close to 90. So it's just a slight bit north of east where this transit's going to occur. Altitude, with the horizon being 0 and 90 degrees straight up. So it says the altitude is 8.7. So it's going to be less than 10 degrees above the horizon in the northeast. That's what that's telling us. The center line distance is the distance of the transit from the center point of the sun or the moon. The visibility path width has 36 kilometers. That's about 30 miles. So 15 miles in any direction from your house. Of course, this one happens to be right on. The duration is how long is the transit going to last. Here it's 2.57 seconds. And the chord length is basically a line across the disk. So with the sun being about 30 arc minutes in size, it shows 30. There we go. 30.9. So the moon in this case is going to be 30.9 arc minutes across. And the transit chord length is 30.9. So it's actually, that tells you it's actually traveling right through the center. Now you see right here, it shows show on map and more information. Well, let's take a quick look at those. Show on map, here's what you see when you click show on map. Here's a map that shows primarily roads and highways, which a lot of people like to use. That's my favorite method of viewing the map. You can also do a satellite map if you'd like, which is this view down below. And you can see the little red dot. That's my location for this particular eclipse. And as you can see, I'm almost exactly right on the center line. But say your friend calls you up and says, hey, I just live a couple blocks from you. How's it going to look for my location? Well, you can click on that location where your friend lives, and it'll tell you. So where I'm 0.21 kilometers from the center line, he would be 0.42. So it'll tell you the circumstances for different locations just by clicking anywhere on this map. I find that very useful, especially if you get one where you're not on the center line. Let's say you're right here. Well, you can move around here, and oh, look, there's a school right there. Let me click that, and I'll go to that school parking lot since school's out of session, and I'll set up there. So it's a real handy feature. Now, if you click on the more information, here's the information that we already saw, and here's so much more information. Some of this is useful, some's not. If you don't have RA and DEC circles, you really kind of don't need that. You really don't need the velocity. That's just what's used in determining how long it's going to take for it to transit the sun. One thing that is important here is the moon's angular size. It's going to tell you how big the moon is going to be at the time of the transit, and how much larger it's going to be than the space station itself. And another important thing is the ISS will be illuminated. Sometimes you're going to see the ISS being illuminated, and it'll appear as a bright white ISS, or it won't be illuminated, and it's going to appear as a dark, almost like a shadow going across the face of the sun or the moon. Now, remember we talked earlier about prediction accuracy. You know, as the space station is traveling around the Earth, it's in an orbit, and the atmosphere is pretty thin there. But let's say we have a big CME come from the sun, and it ionizes the atmosphere, and the ionization moves out into space, and now the space station's going through an atmosphere that's thicker than it was a little before. Well, that's going to put drag on it. It's going to slow it down, and it's going to lower the orbit. And if that happens, then the space station's not going to be where they said it would be. Of course, they're going to hit their thrusters and move the space station back up into the orbit they want it in, but it still may not end up. So it's always a good idea, like the day before or even the day of the transit, to go run the program again and get up to date, accurate times. Okay, the second thing I get asked frequently about ISS transits is, what kind of telescope do I need? I don't know, if you're like this guy up here on the left and you only have one telescope, well, then the kind of telescope you need is the one you have, because almost any telescope will work. Others may work better, others not as good, but a good rule of thumb is the equipment you have is what's best for you at the time. If you're like me and you got bunches of telescopes at your disposal, then you can actually determine which one would be optimal for shooting the ISS. Same with filters. If you're shooting a ISS transit on the sun, you're going to need solar filters. Now, whether that's a Botter, wedge, whether that's a Daystar quark or a quantum, or just a plain white light mylar film, it all depends on what you have. If you don't have any solar equipment, the best thing to do is go out and quickly buy a piece of mylar or a glass filter if you wish. Whatever you have, again, is best. Cameras, if you have a DSLR, they work. I don't recommend using a DSLR because they have some drawbacks, which we'll get into in a minute. I recommend you use some kind of a CMOS or CCD camera, like an imaging source camera, one of the point gray cameras, one of the ZWO cameras, one of the cameras that's capable of capturing video frames in an uncompressed format. Okay, so again, we have an angular size of the space station, and we have the size of the space station. So if you look here, I've got a 3-inch, 4-inch, 5-inch, 6-inch refractors, a 6-inch Ritchie-Crichton, an 8-inch Newtonian. So we need to know the aperture of the telescope we want to look at, the focal length, and the focal ratio. In addition, we want to know what cameras we have. Here's the ZWO ASI 174, the 120, the Canon 60DA, and the imaging source DMK 31. And we need to know the array width, height, pixel pitch, and width and height of the actual sensor itself. And once we learn this stuff, and I just went into the manual, got all this information, and entered it into an Excel spreadsheet, and then pumped in formulas, and it gave me results so I could see what the image scale and arc minutes for a camera at prime focus of each telescope would be, and what the image scale per pixel in arc second for a camera at prime focus would be. So this I want to look at to see how big the moon's going to be. And this I want to look at to see if my telescope's capable of resolving the International Space Station. Now, if you want, you don't have to go to all this length, but you can take your telescope, you can look up the aperture and the focal length and the focal ratio of it, and you can get this information for whatever camera you have. It's out there on the web. And then you can go to one of these sites down here at the bottom, Astronomy Tools or starizona.com pixel resolution and field of view calculator, and you can type in your information and they'll spit back these numbers for you. So okay, we know that the moon's angular size is 30 arc minutes across. So let's look here. We need a camera we're going to be able to see at least 30 degrees or 30 arc minutes. Now if we start here in the ZWO column, we can see the Orion ED80 is going to be 80 by 50. So that's, the sun's going to appear kind of small at 30 arc minutes across. The Lunt going to be 55 by 35. That's a little better. 21 by 16 with the Wolensack, that's not quite big enough. 39 by 25, now that's good if we don't have a full moon. We look at the other cameras and we can see what the field of view. Now here with the 8-inch or the 6-inch Explorer Scientific, I'm sorry, the Orion ED80. With the DMK31, we're not going to get 30 by 30 on any of them. So we don't really want to use the DMK31. The Canon, oh gee, 194, 136, 80, and the sun or moon's going to appear way, 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 way too small with these. So we don't want to use the Canon 60DA here. The ZWO ASI 20, almost everyone except this one barely will fit the moon in. So I'm guessing at this point, the ZWO ASI 174 camera is going to be my best bet. For me, that's what's going to work best. And probably, I'd say this one here, 55 by 35. So I'm going to want to use my Lunt Engineering 102 and my ZWO ASI 174 camera to get me a 30 degree by 30 or 30 arc minute by 30 arc minute field. Now the angular size of the space station is going to be 17 arc seconds, almost 18 arc seconds. So at this point, any of the scopes I use with the 127, any of those are going to be fine, except look at the Wollensack 127. Now it's going to be giving me 0.99 arc seconds resolution, which is great. That's really fine resolution. But what about the seeing? If the seeing's not sub arc second resolution, then I'm not going to see that resolution anyways. But we kind of can't depend on the sky and the seeing being what we want it to be. So that's not so much a factor as making sure that we have the right resolution. Now, another thing to consider, the space station, if it's directly overhead, it could be as close as 390 kilometers away. If it's way out on near the horizon, it could be 12, 15, 1700 miles away from us, at which point it's going to appear a lot smaller than it is when it's at 390 kilometers away. So one important aspect of shooting the ISS Transit, and we alluded to this before, was timing. Timing is critical. When you have something that only lasts 0.7 seconds, it's very critical. This particular transit's going to last almost 3 seconds. So we have a lot of time there to play with. You could probably take a DSLR out there, and within 3 seconds, you're going to capture it. But in 3 seconds, how many times can you match the camera? Maybe 3. So you might catch 3 images. If you have a DSLR, you can put it in video mode. But if it's like mine, it's only going to capture 8 frames per second. And then it's going to stop and write to the card. So it gives me a little more leeway. I can actually count down to the time and then go 1001 and hit the button, and I'm somewhere near the middle of the transit, and I should get 8 frames somewhere near the middle of the transit. But because the frame rate's so slow, that's why I recommend you don't use a DSLR. If that's all you have, yes, use it. But if you can get one of these other cameras, well, just look at what you can do. This imaging source, you can capture 30 frames in a second. So at 3 seconds long, you're going to get 90 images of the space station moving across the sun or the moon. If you go with the ZWO 120, you get 45 frames per second. So there you're getting over 100 images with the space station. With the ZWO 174, and this is the one I use, you get 175 frames per second. That's about 500 images of the space station crossing in front of the sun. So, and you don't have to be as accurate. If you can start this thing up like 15 seconds beforehand and let it run all the way through, you're doing good, because you can shoot up to 30 seconds with this thing before it starts giving you problems. The ZWO 120, same thing. You can shoot about 30 seconds with it. The imaging source, yeah, you could probably go 30 seconds with it too. So any of these cameras, you can actually, timing's not as important, because you can start it 10 seconds beforehand and let it run for 30 seconds, knowing that somewhere in there you're going to have a good set of images. The other thing to consider when you're going out to shoot is, if you're using a laptop, which you're going to be if you're using one of the CMOS CCD type cameras, you're going to need a laptop with it. And even if you're shooting with the DSLR, as you can see I am in this picture, it's still nice to project that image onto a 15-inch monitor on a computer screen and see it quite big, and you can focus really well. And if you put your computer inside a box and throw a blanket over top of the box and yourself, and get it to where you can see really good and have a lot of contrast on your monitor, that's going to help you a lot. If you've got that monitor out in bright daylight, it's going to be really hard to see it. So build yourself some kind of an enclosure. Okay, we already said I used the ZWO1 or ASI 174. It's a mono camera, but you can colorize your images later if you'd like. Filters. Sometimes you're going to need a neutral density filter, especially if you're shooting the moon and it's full. It's going to be really, really bright, and you don't want to overwhelm your camera sensor. So I use the NPAE Nottingham Precision Astro Engineering's filter set, and I can just slide filters in and out easily and on the go. And next, when you get all this done, you're ready to capture your image. So again, if you have the capability, connect your camera to a laptop so you can get somewhere in dark and see in high contrast, get good focusing. And now to do this, you're going to need a software capture program. And there's two that come to mind. Fire Capture and Sharp Cap. Both, they're very similar programs. A lot of people like Fire Cap, a lot of people like Sharp Cap. It's a matter of personal preferences. I'd say if you've never used either, download both and try them both. See which one you think you like best. If you are using a DSLR, I'd download Backyard EOS, and that's for a Canon camera. I think it's called Backyard NIK if you have a Nikon. But these programs are free, and there's a couple links there that you can follow to go to those links and download the program. Next in the capture process, I got to say, focus is critical. That's why I tell you to get a box or some kind of enclosure, get inside so you can see the contrast on your screen. Make sure your focus is good and sharp and your framing's just right. And pay a lot of attention to focus because you're only going to get one chance. Framing, depending on your pixel pitch and your camera resolution, as we talked about earlier, it's going to determine the size. So if you are using real tight parameters, make sure your framing is just right, like we did here, so you're not missing too much of the moon if you're in real close. I usually shoot between 2,000 and 3,000 frame serial video, which I stack later. And you got to think about your gain settings. That's like your ISO settings on a DSLR. You want to move your gain settings to increase your exposure, but you got to take care not to overexpose your image. Sharp Cap has a handy feature called Highlight Overexposed. And if you get any part of your image become overexposed, it'll start flashing white. So I think that's a real good feature. Yeah, and again, as I said earlier, I recommend shooting around 30 frames per second as a minimum for solar and lunar imaging. And of course, once you get your pictures, it's a good idea to capture calibration frames, which you'll use to register and align and stack your subs. Then you can go into your photo editing program and sharpen and stretch, process your image. But we're not going to get into all that here today. That's going to be another presentation down the road in the future. That's it. That's my program. I hope you enjoyed it, learned something. And guys, if you get out and, or guys and ladies, when you do get out and shoot one of these, please send me a email and say, hey, look what I did. I'd really love to know that someone actually went out and got some pictures and is sharing them with people. So there's my email address. And that's it. Are there any questions?